In this video, we're going to explore the graphs of polynomials. In particular, we're going to look at a graph and use that to figure out what degree it is, what kind of end behavior it has, what the leading coefficient looks like, and, if possible, write the equation. So, we'll start off with this first example. When we're trying to look at a polynomial graph, the clues we look for are the roots or the zeros. And when we look at this one, we see we have 3 roots. 3 roots means we have an odd degree polynomial. It is at least third degree. Next thing we're going to look is for those turning points. We look here, we have one there. We have one down here. That gives me 2 turning points. And we know that the degree of the polynomial has to be greater than the number of turning points. We don't always see them all when we look at the graph, but in this case, we know we're still at least third degree since we have 2 turning points. Finally, we're going to look at the end behavior. And we know as we're going off to the right, as x is approaching infinity, y is going up. As we're going to the left, as x is approaching negative infinity, we're going down. This fact that this is going in opposite directions tells us again this is going to be an odd degree. And being an odd degree, it works kind of like a line. And since this one is going from the bottom left to the upper right, that's like a line with a positive slope. So we can say right now that this graph has this, my guess is going to be a third degree with a positive leading coefficient, or a is going to be greater than 0. That's my guess about this. Now, how do we write the equation? We're going to take a leaf out of the quadratic page for this, because we have here 3 roots. I can find all of those 3 roots, so I'm going to write this in factored form. And in factored form, a third degree polynomial is going to have 3 factors: x minus root 1, x minus root 2, x minus root 3. It has a leading coefficient. And my equation is going to look something like that. Now, looking at the graph, I can read what those roots are. This one is at negative 1, 0. This one is at positive 1, 0. This one is at positive 2, 0. So my equation is going to be a times x minus a negative 1 times x minus a positive 1 times x minus a positive 2. And we're most of the way towards getting our equation. All we need to do now is find my a value. I'm going to find a point, plug it in to find my a. Since I'm only missing one value, one point can help me find it. So I look on my graph and I see this point right here. The y-intercept, or 0, 5, is a point I can read nicely from the graph. I'll just plug that into my equation. 5 equals a times 0 plus 1 times 0 minus 1 times 0 minus 2. Or 5 is going to be a times 1 times a negative 1 times a negative 2 is 2. So a is going to be 5 halves. And that is indeed greater than 1. That works with what I expect. So the equation of my graph now is going to be y equals 5 halves times x plus 1 times x minus 1 times x minus 2. Using exactly the same things we use to find factored form for a quadratic, we can use this on this polynomial. So let's look at another example. We look at this example. Again, we're going to start off with the roots. Got a root there, got a root here. That's what we call a double root because it's just touching the x-axis. Now, if you're not positive or you forget about that, let's look at this end behavior. We're going up on this end and we're going up on this one. This is looking like a parabola, which means this has to be an even degree. If it's an even degree, it has to have an even number of roots. So we count that root as twice. So we have a root here at 4, 0. We have a root here at 2, 0. And here we're going to have two roots, negative 1, 0 and negative 1, 0, to give us our 4 roots. My end behavior, as I said, agrees with the idea of an even degree. If we look for turning points, this root is a turning point. Here's a second one. Here's a third one. 3 turning points makes a 4th degree polynomial look reasonable. So we're going to assume on this one 4th degree. 4th degree with, again, a positive leading coefficient. So again, let's write this equation because we have all the roots. So I'm going to come along and say y equals a times x plus 1 times x plus 1. I have to include that twice because it's a double root. X minus 2, x minus 4. Again, once we have all of those roots, all we have to do is find that a value. So once again, to find the a value, I'll pick a point, and this y-intercept looks like a nice point to use again. If I can use the y-intercept, I like that. I like plugging 0 into an equation. It's usually easier to work with. It makes a lot of the math easier. So we plug in that 4 equals a, 0 plus 1, 0 plus 1, 0 minus 2, 0 minus 4. So 1 times 1 is 1 times negative 2 times negative 4 gives me 8. So 8a equals 4. So a equals 1/2, giving us our final equation, y equals 1/2. I'll do the x plus 1 squared, since I have it twice. X minus 2, x minus 4. And again, a was supposed to be bigger than 0. A is indeed bigger than 0, so this looks reasonable. So let's look at this last equation, or this last example. When we look at this one, I see 2 roots. But as I look at the turning points, I got 1, 2, 3. 3 turning points, so I know I'm at least 4th degree. I can't be 2nd degree. I got this funky stuff going on up here. As I look at the end behavior, again, my end behavior, I'm going up to the left and up to the right. So this is looking like a parabola. So this is an even polynomial. And again, we have a positive leading coefficient. But we know this has to be at least 4th degree. And this is what gives us problems on this one. We know the leading coefficient is going to be positive. But the fact that we only have 2 real roots, that means my other 2 roots are going to have some imaginary part. We got 2 complex imaginary. So if I want to write this out in factored form, This is going to give me y equals my a value, x minus root 1, x minus root 2, but here comes the joy. The other two roots are going to be in the form a plus or minus bi. So I'm going to use a different letter here. Let's go C instead of A, so I don't have too many A's in here. So this is going to be x minus C plus bi, x minus C minus bi. This becomes a whole lot more complicated problem to work at, so we're just going to right now say, yeah, it might be possible. We're not going to mess with it. So this method works really well if I can find all the real roots. If I have those complex roots in there, I can identify the degree, but it's a whole lot more hassle to write the equation. So we might look at other ways to do that.